Okay, so this is week 10. All right, today is Tuesday, October 20th. We're basically going to finish chapter 4, which is its own thing, right? It's its own homework assignment. It's a short homework assignment. Back when I had in-class exams on campus, this was my apology exam, which was meant to be an easier one. The homework for chapter 4 is due next Tuesday in 7 days. Well, actually 8 days. It's due Wednesday, October 28th. Right. Although we will discuss the homework not just at the end of Thursday, but also for all of Tuesday, right? All of Tuesday, October 27th, next Tuesday. And it's due the next day by midnight that day, Wednesday, October 28th. All right. So we're going to finish chapter 4 today, but that blends into chapter 5, which is Analytic Trig. So it's a very natural blend over. I'll continue with 5 on Thursday. And in fact, 5.3 can actually help you with some of the problems in these parts over here. So section 5.3 might actually be helpful. You might want to do 5.3 first in order to really master some of the ideas here. So I do encourage you to do 5.3 actually by the time we get to here. 5.3 is not due by then, but I think it's good for you to get a head start. 5.3 has good ideas that will continue on ideas we'll talk about here. This will help on your homework for chapter 4 actually. We will talk more about the homework for chapter 4 and 5 if you wish at the end of Thursday, all right? And then again, the homework will be discussed and will be due next week. This Friday is the withdrawal deadline, all right? After that, you're committed to a grade like A to F, all right? Right now, I am grading the chapter 1 homework, and I do hope to get that back by the withdrawal deadline. All right, so any questions before we proceed? Any questions before we proceed? We're going to begin with a review of inverse trig from last time, by the way. That should help a whole lot. Okay. So we're going to start with a bit of a review. Any questions so far? Okay. Yeah, I'll take questions on homework after class. I always do. All right. Any questions? Unless you feel it's a roadblock. If it's a roadblock, we should address that now. But I'll take questions after class. All right. Any questions? Any questions? Any questions? Again, I'll take homework questions after class, as I always do. All right. Okay, so let's start off with our review. Okay, so I'm going to review inverse sine from last time. We are recording. Yes, we are recording. All right.
But there's a problem when we try to invert this and get.
Okay, first of all, let's start the beginning, crank up the volume.
Now, in the beginning, we have y equals sine of x. Let's consider the graph of y equals sine of x, the sine wave. But there's a problem when we try to invert this and get an inverse function, inverse sine of x. The problem is that even though this graph passes the VLT, the vertical line test, so we have a function here, the problem is that it fails the HLT, the horizontal line test, which means that this function is not one-to-one. It's not invertible. It fails the horizontal line test. I can take a horizontal line here that intersects the graph in more than one point. In fact, infinitely many points. So what we need to do is that we need to restrict this sine wave. We need to restrict the domain of sine of x in such a way that we follow two conditions. What should this restricted domain be? It should be an x interval on which the sine graph, first of all, passes the HLT, the horizontal line test. That means we can take an inverse. That's an inverse function. And it has to be as tall as the original graph, meaning that the range is the same as before. Because I could say, hey, the origin, the point 0, 0, if I grab that, that passes the HLT. But that's pretty lazy. We would like something bigger than just a point. We would like something as tall as the original graph that has the same range, but a piece of the graph that will pass the HLT. So we want a piece of this sine wave that's as tall as the original graph, it has the same range, but passes the HLT, the horizontal line test. Now, we all agree across the planet that we start at this point, negative pi over 2, comma negative 1, and then where would we stop? Well, we want to pick up the entire range, so we have to keep going, going, going. We want the entire range, and we're going to stop where? We're going to stop here, at this point here, at pi over 2, comma 1. Because we want to capture the entire range for the sine function from negative 1 to 1. Technically, it's a new function here because we're restricting the domain. For the original sine function, the range was from negative 1 to 1. The domain was all reals, but we're now restricting the domain to this closed interval from negative pi over 2 to pi over 2. We have the same range as before. Now, we don't want to go any further because then we're going to we're going to fail the horizontal line test. So we don't want to go any further than this point. Okay, so we all agree that we're going to grab this red piece of the sine wave from this point here to this point here. And it goes to the origin, 0, 0. So then, how do we go from this restricted sine function to an inverse sine function? We can invert this because it now passes not just the VLT, but the HLT. So remember a key basic principle. Actually, there are 3 basic principles. The domain of one function becomes the what of its inverse function. The domain of a function, a one-to-one function, like this now, becomes the range of its inverse function. Second, the range of this function becomes the domain of the inverse function. And also, the idea that the point A comma B on the original graph becomes what point on the inverse graph? The point B comma A. The idea being that inputs and outputs switch. So based on this red graph here, how do we invert this red graph to get the blue inverse graph? I'll take a copy of my notes here. And here we go. Again, we switch the domain and the range. Let's look at this grid. The restricted domain for sine of x, we just determined that on Desmos. The restricted domain, the x-coordinates go from negative pi over 2 to pi over 2. The domain for the restricted sine function becomes the range for the new inverse sine function. Likewise, the range for both the original and the restricted sine function, the y-coordinates we pick up, went from negative 1 to positive 1, the y-coordinates. The range for the sine function now becomes the domain for the inverse sine function. The domains and the ranges switch. And these are all closed intervals. So observe, the old domain went from negative pi over 2 to pi over 2. That's the new range, from negative pi over 2 to pi over 2.
So I reviewed inverse sine there. Any questions? Any questions? All right, reviewing the inverse trig functions and moving on.
Hi everyone, I want to discuss a shortcut in section 4.7 that will help you figure out the ranges of these inverse trig functions quickly. Because if I were to ask you, what is the range for the inverse sine function? You might go, oh no, I guess I should look at the original sine function, figure out what piece I need, the restricted domain I would want, and then that becomes the range. It might take a while. So let's talk about principles. So when I pick a piece of this original sine wave that passes the HLT and it has the same range, I'm picking this red piece here. And when I consider this restricted sine function, what am I doing? I'm getting a restricted sine function where there is a one-to-one relationship between the x-coordinates here and the y-coordinates here. The x-coordinates here basically correspond to angle measures in radians from negative pi over 2 to pi over 2, and the y-coordinates correspond to sine values, y-coordinates on the unit circle. So I want to have a one-to-one relationship between angle measures and sine values. So what's our shortcut? Remembering the ranges of inverse trig functions. Inverse sine. All right. I want an interval of angle measures in radians where I will pick up each sine value exactly once. Sine values correspond to y-coordinates on the unit circle. -1 here, +1 here. Well, you agree that if I consider the right half of the unit circle, I pick up every y-coordinate, every sine value between -1 and +1. And what is the interval of angles in radians that I normally associate with the right half of the unit circle? Well, the closed interval from the angle I associate with the south pole is usually -pi/2, comma, the angle I associate with the north pole is usually +pi/2. And guess what? That's the range for the inverse sine function, is this interval of angle measures in radians where I pick up each y-coordinate along the unit circle exactly once. So there's a one-to-one relationship between the angles in here and the y-coordinates in here between -1 and +1. For example, there's only one angle in here with a sine value of 0, 0. There's only one angle in here with a sine value of 1, pi/2, and so forth. Well, what about cosine and inverse cosine? What is the range for inverse cosine? Well, look at the unit circle. Cosine values correspond to x-coordinates. How do I pick up each x-coordinate on this unit circle exactly once? And what is the interval of angles I would normally associate with that? Well, to pick up each x-coordinate on this unit circle exactly once, how do I pick up each x-coordinate from -1 to +1 exactly once on this unit circle? I'd probably take the top half of the unit circle. And what are the angles I normally associate with this top half? The closed interval from 0 radians over here to pi radians over here. And that's going to be the range for inverse cosine. And there's a one-to-one relationship between the angles in this interval and the various cosine values, the various x-coordinates on this unit circle. There's only one angle in here whose cosine value is 1, 0 radians. There's only one angle in here whose cosine value is -1, pi radians, and so forth. Now, what about inverse tangent? How do I pick up every tangent value exactly once? Tangent is slope. How do I pick up each slope value exactly once? In such a way where I don't have to worry about undefined slopes. What piece of this unit circle would I look at, and what angles would I want to consider? All right, how do we pick up each tangent value or slope exactly once? I would probably take these angles in quadrants 4 and 1. You would agree that I pick up negative slopes, all possible negative slopes in quadrant 4. I pick up a slope of 0 at 0, angle 0, radians. I pick up all possible positive slopes in quadrant 1. But remember, tangent of pi/2 is undefined, and tangent of -pi/2 is undefined. So I don't want to reach these endpoints over here. How do I pick up each tangent value or slope value exactly once? I consider the open interval from -pi/2 to +pi/2. And unlike the other ranges, this is an open interval because I don't want the endpoints over here. This is the range for inverse tangent because there's a one-to-one relationship between every angle in this interval and every tangent or slope value between here and here. If you give me any real number, any negative real number, 0, or any positive real number, there's only one angle in here with that corresponding slope or tangent value. Here's the range for inverse tangent. So to quickly figure out the inverse trig function's ranges, consider the unit circle. What piece of the unit circle would give you each value of the original function for sine, cosine, or tangent, and then figure out what angles you'd normally associate with that part of the unit circle. All right, next time, we're going to talk about evaluating these inverse trig functions.
Okay, so remember, these are shortcuts for figuring out the ranges of the inverse trig functions. So you don't have to go all the way back to, oh gosh, if we start off with sine, cosine, or tangent, which piece do we cut off? How do we invert it? Da, 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 da. So these are meant to be shortcuts. All right, we're going to talk about evaluating inverse trig functions next. Any questions? Any questions? We've talked about domains and ranges so far. Any questions? And graphs. All right.
Hi, everyone. We're continuing with section 4.7, and we will now evaluate inverse trig functions. Again, in the beginning, let's talk about our big daddy sine function. Imagine this sine button on your calculator and put your calculator in radian mode. Now, this sine function will let us input basically angles in radian measure. They can be thought of as just real numbers, but let's think of these inputs as angles in radian measure. So for example, we can input pi over 2 radians and evaluate the sine of pi over 2. Well, the sine of pi over 2 is going to be what? It's going to be 1. Sine of pi over 2 is 1. In case you forgot why, we can think of the unit circle. Pi over 2 is this point up at the North Pole. We want the sine value. What's the y-coordinate of that point? It's going to be 1. Sine of pi over 2 is 1. Also, if you remember that trick we talked about in section 4.2, SIN. At pi over 2, the sine of pi over 2 radians is 1. Think of that I representing 1. All right, sine of pi over 2 is 1. We input pi over 2 into your calculator, you press the sine button, and the output is 1, which is a sine value, a number in the range of the sine function. Now let's say we want to invert this process. What if we take the inverse sine button on our calculator? It might be a shift sine operation, for example. But we take this inverse sine button or function on your calculator. We see 1 in our calculator display, or we input 1. What then will be the output? Well, if you have a fancier calculator, it should output pi over 2 radians, or just pi over 2. And why is that? Because the inverse sine, or arc sine, of 1 is pi over 2. And that makes sense because of 2 reasons. Because the sine of pi over 2 is 1. As we mentioned earlier, that's what this was saying. Sine of pi over 2 is 1. If you input pi over 2 into the sine function, the output is 1. Now I'm claiming that if you input 1 into the inverse sine or arc sine function, same thing, the output is going to be pi over 2. In part because sine of pi over 2 is 1. Remember that when you write down an inverse statement, you're basically switching the inputs and the outputs. Sine of pi over 2 is 1. So we may be able to say that arc sine of 1 is pi over 2, or inverse sine of 1, is pi over 2. But there is a second condition. We have to make sure that this angle that's being spit out is in fact in the range of the inverse sine or arcsine function. Remember that any function is only allowed to spit out a value, is only allowed to output a value in its range. Well, the inverse sine or arcsine of 1 is pi over 2 because pi over 2 is in the range of inverse sine. Inverse sine is allowed to spit out pi over 2. So there are two reasons why the inverse sine or arcsine of 1 is pi over 2. Because sine of pi over 2 is 1. This switching works. One here, one there, pi over 2 here, pi over 2 up there. And because pi over 2 is in the range of the inverse sine function. Now remember, pi over 2 was in the restricted domain of the sine function. Remember when we restricted the sine function, we went from negative pi over 2 to pi over 2. Pi over 2 was legal. It was a legal input. It was in the restricted domain. And when that happens, this loop-to-loop works perfectly. We start with pi over 2, input into the sine function, the output is 1. And then if you take 1 and input into the inverse sine function, the output is pi over 2, which is the same as the original input at the very beginning. This loop-to-loop works as long as pi over 2, as long as this angle here, is in the range of the inverse sine function. Then this works perfectly. Basically, we're saying here that the inverse sine or arcsine of the sine of pi over 2 is pi over 2. You input pi over 2, and the ultimate output is pi over 2. We'll talk more about these inverse properties later. In the next video, we're going to evaluate some more inverse trig functions.
So any questions about this loop-to-loop here? Because this is key to understanding how these functions are inverse functions, right? They undo each other. Inputs and outputs switch. Any questions? Any questions?
Hi, everyone. We're evaluating inverse trig functions in section 4.7. Remember that for this Big Daddy sine function, the inputs are basically angles, and the outputs are basically sine values, numbers between -1 and +1. But for the inverse sine function, the inputs are sine values, and the outputs can be thought of as angles. By the way, the outputs of these inverse trig functions should technically be written in radian measure or as real numbers. Later on, when we do applications, we may write these in degrees, like 90 degrees. Again, why is the arcsine or inverse sine of 1 equal to pi over 2? When we input 1 here into inverse sine, why is the output pi over 2? For two reasons. Because sine of pi over 2 is 1. Remember, we have the switching between inputs and outputs for the inverse statement. And because pi over 2 is in the range of the inverse sine function. That's really critical. Functions can only output values in their ranges. So once again, if you are asked to evaluate the inverse sine of 1 or the arcsine of 1, how would you go about doing that? You could think of it as a kind of box method, like when we did logs in chapter 3. The inverse sine of 1, is what? Answer in the box there. Well, the sine of what is 1? The sine of what is 1? Remember when we went to from log form to exponential form? The sine of what is 1? It's like a zigzag. Now, a student might say, well, wait a minute. There are infinitely many angles that will work. Think about the graph of y equals sine of x. By the way, on Desmos, if you use the wrench here, not only can you use projector mode to make things clearer, but on the x-axis, you can use a step size of, say, pi over 2, or some fraction of pi, in order to get these kinds of values as tick marks. All right, y equals sine of x. We want to know for what angles will the sine value be 1? Well, sine of pi over 2 is 1, but also sine of 5 pi over 2 is 1, sine pi of 9 pi over 2 is 1, sine of negative 3 pi over 2 is 1. There are infinitely many angles whose sine value is 1. But remember, we're restricting the sine function to this restricted domain from negative pi over 2 to pi over 2. We're only supposed to consider this piece of the sine wave, only the piece from this point, negative pi over 2, negative 1, to this point, pi over 2, 1. And if you look at this red piece over here, of these various angle measures for x, the only angle whose sine value is 1 is pi over 2. So we have to fill in this box with pi over 2. Because that's in the restricted domain. So the answer here is pi over 2. A faster way of seeing that is if you look directly at the inverse sine function. Here's a graph of the inverse sine function. What is the inverse sine of 1? The answer, the output, is pi over 2, the y-coordinate of this point. The inverse sine of 1 is pi over 2. Y equals arc sine of x. The inverse sine of 1 is pi over 2. Why? Because pi over 2 is in the range of the inverse sine function. So again, even though it's true that sine of pi over 2, 5 pi over 2, and so forth, even though there are infinitely many angles whose sine value is 1, there is only one angle whose sine value is 1 and that is in the range of the inverse sine function. Pi over 2. 5 pi over 2 is not in the range. If you say that the answer to this is 5 pi over 2, that's no credit, because you do not know the range of the inverse sine function. Or you don't know that a function is only allowed to spit out outputs in this range, and that's bad either way. The inverse sine of 1 is pi over 2. It's not 5 pi over 2. You have to keep the range in mind. That's why we kept hitting that theme like in previous videos. We'll do some more examples in the next video.
All right. Any questions? Any questions? And before I go on, I had to amend this one. It's really inverse sine. At least you remember it. But again, it's really what's your inverse sine, okay? That's how much of a pedant I am. All right. Not to say they work, but they're very funny. That's right. Any questions? Any questions? See, you remember it, right? You remember it. It's horrible, but you remember it. All right. Yeah, extra credit if you use these lines at a bar. No, I'm kidding. Don't go to a bar. All right.
Hi, everyone. We're continuing with section 4.7 on evaluating inverse trig functions. First off, here's a cute meme I found online. Actually, it should say, hey girl, what's your inverse sine? Because the inverse sine of 1 is pi over 2. But let's get back to business. All right. Let's evaluate the inverse sine, or the arc sine, of negative root 2 over 2. And I'll give you 20 seconds to figure this out. I'll give you a few hints first. Again, what are we looking for? We're looking for an angle. We're looking for an angle. The inverse sine, or arc sine, of negative root 2 over 2 is what angle? First of all, you agree that negative root 2 over 2 is a sine value. In fact, it's a famous sine value. It's a famous special sine value. It's not like -10 or something. So we will have an answer. It will not be undefined. So what we want then is an angle such that the sine of box, the answer, is -√2/2. You're looking for an angle whose sine value is -√2/2. And it has to be in the range of the inverse sine function. In the range of the inverse sine function, arcsine. So two conditions here. The sine value has to be -√2/2, and it's got to be in the range of inverse sine or arcsine. 20 seconds, go. Okay, so let's start to figure this out. Now, we want an angle whose sine value is -√2/2, but that negative sign makes things a bit more difficult for us. So instead, why don't we do this? The answer is not going to be quadrantal, because -√2/2 is not the sine value for a quadrantal angle. So let's find the reference angle. Okay, find the reference angle for the answer. Remember, the answer is basically like an angle. So I want to know a nice acute reference angle such that the sine of that angle is +√2/2. Positive √2/2. So consider the unit circle. I want an acute reference angle whose sine value is +√2/2. And I hope you remember that that's going to be π/4. In fact, that's the inverse sine of +√2/2. But we want the inverse sine of -√2/2. And that's going to be a brother for π/4. But in which quadrant? Well, in what two quadrants is the sine value going to be negative? In what two quadrants will the sine value be negative? In quadrants 3 and 4. It's like y coordinate. The sine value is negative in quadrants 3 and 4. But now wait, we also need our answer to be in the range of the inverse sine or arcsine function. And what is the range for the inverse sine function? From -π/2 down here, I'll put this in red. From -π/2 down here at the South Pole, up through +π/2 up at the North Pole. So I want an angle in either quadrants 1 or 4. So which is the only quadrant where the sine value is negative and it's going to help us with the range for inverse sine? It's got to be quadrant 4. We need a brother for this angle in quadrant 4. So a student might say, oh, I guess the answer is going to be 7π/4. Because the sine of that is -√2/2. That part's right, but is this the answer? The answer is no, that's not the answer. That's 0 credit. Because 7π/4 is not where? It's not in the range of the inverse sine function. Your answer must be in the range of the inverse sine function. And 7π/4 doesn't cut it. So what coterminal twin will cut it, will work? The range for inverse sine goes from negative pi over 2 to pi over 2. The only brother here in quadrant 4 that's going to work is going to be negative pi over 4. And that is going to be the answer. We know that sine of negative pi over 4 is negative root 2 over 2. And it is in the range of the inverse sine function, or arcsine. It's between negative pi over 2 and pi over 2. So we conclude that this is the answer, the value for this. Sine of negative pi over 4 is that, and it's in the range of the inverse sine or arcsine function. Negative pi over 4 is our answer. Next up. How about the inverse sine of 3, or arcsine of 3? The inverse sine of 3 is what angle? Well, wait a minute. The sine of what equals 3? Is any angle, is any real radian measure going to work in this box? The answer is no. Inverse sine of 3 is undefined, or at least it's not real. Actually, imaginary numbers may work, but we're going to keep it real. This thing is undefined. It's not real, as far as we're concerned. Because 3, guess what, is not a sine value to begin with. In a way, that's the very first step. Ask yourself, is 3 even a legitimate sine value? It's not. It's not a sine value. Remember in the loop-to-loop picture that we had way up here, okay? The sine function outputs values between -1 and 1. That's the range for sine. And for the inverse sine function, we're only allowed to input sine values, values between -1 and +1. If you input something on the outs, like 3 or -3, then the result is undefined. It's not real. 3 is not a sine value. No go. Likewise, the inverse cosine of 3 or the arc cosine of 3 will also be undefined or not real, because 3 is not a cosine value either. What about inverse tangent of 3, or inverse tangent of 10, or inverse tangent of 100? I'll skip all the way down here, actually. The inverse tangent of 10 is defined. It is real, about 1.47 radians, which, by the way, is going to be pretty close to pi over 2. Why is that? Now remember, if this is a positive, legit trig value that we're looking for, then the answer is going to be either an acute angle or quadrantal. All right, now we want an acute angle in this case that corresponds to a slope of 10. So it's going to be a pretty steep angle. And that's why 1.47, the approximate answer, is pretty close to pi over 2. It's pretty close to pi over 2, which is about 1.5 to 1.6. But yeah, the answer to this is an angle in radian measure corresponding to this ray, this terminal side, with a slope of 10. This angle does exist. So inverse sine of 10 is undefined or not real. Inverse cosine of 10 is undefined or not real. But inverse tangent of 10, that is real. It's about pi over 2. It's actually more like about 1.47 radians. It's a pretty steep angle. Now, going back to this example here. Evaluate the inverse cosine or arc cosine of -1/2. "20 seconds, go." So let's try to figure this out. All right. So the inverse cosine of -1/2 equals what? First of all, I need an angle such that cosine of that angle is -1/2. And you agree that there are angles whose cosine values will be -1/2. In fact, -1/2 is a very famous special cosine value. Let's get to first base here, right? I mean, -1/2, that is a legitimate cosine value. This is, in fact, a cosine value. Right. Again, if that were like -3 or +3, we're done. Undefined, we're done. But we are going to have a real answer here. First of all, I need an angle whose cosine value is -1/2. A student might say, wait, there are infinitely many angles that do that. Well, yeah, but we need the one angle in the range of inverse cosine. We need this to be in the range of inverse cosine or arc cosine. And there's only one angle that's going to do that, whose cosine value is -1/2, and that's in the range for the inverse cosine or arc cosine function. All right. Now, first of all, it might help to find the reference angle. You might tell that the answer will not be a quadrantal angle. Find reference angle for the answer. In particular, I want to find an angle such that the cosine of this reference angle is +1/2, because that's an easier question to answer. In fact, you might have a table or a unit circle picture ready-made for this. The cosine of what famous acute reference angle is +1/2? Well, it's going to be sort of to the left. It's going to be the steep angle. It's going to be π/3. That's the reference angle for the answer. But that's not the answer. Okay, it's the reference angle for the answer. It's the reference angle. But wait, in red, we want to get the actual answer. So first of all, cosine of what will give us -1/2? Well, quadrant is key here. In what two quadrants will cosine be negative? Cosine is like x-coordinate on the circle. Cosine will be negative in either quadrant 2 or quadrant 3. The cosine value, or x-coordinate on the circle, will be negative. Now it's a question of range, because the answer has to be in the range of our cosine, or inverse cosine. The range for inverse cosine, remember, goes from 0 radians up through pi radians. So which quadrant does the answer have to be in? The answer has to be in quadrant 2. We need a brother for this point over here. The answer has to be a quadrant 2 angle, because quadrant 3 angles are not in the range for our cosine. So who's the key famous brother we want in quadrant 2 that's in the range between 0 and pi? Only one. 2π/3. That's got to be the answer. We know cosine of 2π/3 is -1/2. And again, 2π/3 is in the range of the inverse cosine or arc cosine function. The range, by the way, is from 0 to pi. So the answer here is going to be 2π/3. And don't put any other angles. If you put any other angles, that might be no credit, because then you don't know what a function is. Remember, a function is not allowed to spit out more than one value. So if you put more than one value here, I have the right to give no credit because you don't know what a function is. That's a problem. Way back in chapter 1. Okay, 2π/3. Next up, we're going to talk about the inverse properties, which will be the subject of the next video.
Okay, so we've been talking about evaluating. Next, we're going to talk about when these things undo each other. Okay, so this might be kind of confusing, so feel free to ask questions in chat. Any questions? Any questions? All right.
Hi, everyone. We're continuing with section 4.7 on inverse trig functions, and we're now going to discuss two groups of inverse properties. Let's remember inverse properties for other functions. So for example, what is the cube root of the cube of x for all real values of x? This is just x, because the cube root function and the cubing function are inverse functions. They undo each other perfectly. What about ln of e to the x? We see here an exponential function rule. We see here a log function. We have here a pair of inverse functions. This simplifies to x by an inverse property. And this is true for all real values of x. So under what circumstances will these be true? When will sine of inverse sine of x equal x? When will cosine of inverse cosine of x equal x? And when will tangent of inverse tangent of x equal x? It's under these circumstances. And what's an easy way of saying this? Basically, x here, the argument in here, is asking the outer function, am I in your range? If the outer function says yes, you're in my range, then the outer function will go ahead and spit that argument out. So, what is the range for the sine function, this outer function? It's the closed interval from -1 to 1. These are the sine values. So if x is in this interval, then x will be the output. Likewise, if x asks cosine, am I in your range? When is x in the range for the cosine function? Again, when x is in the same interval from -1 to 1. These are the possible cosine values. So under these circumstances, the output will be x. When x here asks tangent, am I in your range? Tangent is very liberal. Tangent says, hey, every real number is in my range because any real number can be a slope. Positive, negative, 0, a million, negative a million. The range for the tangent function is all real numbers. So we have these very nice inverse properties for group 1, provided that x, the inside argument here, is in the range of the outer function, sine, cosine, or tangent. Otherwise, your answer will be undefined. For example, if you try to put a 3 here, the inverse sine of 3 is undefined or not real, and you're dead right there. The answer will be undefined. That's the case for these top two. For this third one is very liberal. You can put in any real value for x, and you'll get that result as your final output, because tangent is so liberal. As an example, what if we put a 1 here? I claim that you get 1 as an output. We can see that in the picture we saw earlier. Here's the inverse sine function, down here in blue. If you input a value of 1, that's a sine value, the output will be pi over 2, because the inverse sine of 1 is pi over 2. We've certainly beaten that into the ground. And then, if you take the sine of pi over 2, the result is 1. So we're basically saying that, okay, the arcsine or inverse sine of 1 is pi over 2. That's what this says over here. If you input 1 into inverse sine, the output is pi over 2. And if you take the sine of arcsine of 1, you're taking the sine of pi over 2, and the sine of pi over 2 is 1. So the sine of arcsine of 1 is 1. Arcsine of 1 is pi over 2. You take the sine of that, and you're back to 1. Your final output was your inside input. And again, this works beautifully as long as you have a legitimate sine value. Or if you have cosine and inverse cosine, a legitimate cosine value, it's the same set of numbers, the closed interval between -1 and 1. If you're dealing with tangent and inverse tangent, this could be any real number. And then the final output will be the number, the input. Let's look at some examples. All right, example. The cosine of the inverse cosine of 0.2. The cosine of the inverse cosine of 0.2. The answer will be 0.2 because the inside argument here, 0.2, is asking the outer function cosine. Hey, am I in your range? Cosine says, yes, you're in my range. You are a cosine value. You're between -1 and +1. So I can spit you out, and I do spit you out. The answer is 0.2. It's you. Of course, this works because we have cosine here and inverse cosine there. If you mix up functions, if you have, for example, sine here and inverse cosine in there, then we need to use a right triangle approach, which we'll discuss in a later video. By the way, if we have sine and inverse sine, the result will also be 0.2. Now, cosine of inverse cosine of 10. Well, 10 asks cosine, am I in your range? Cosine says, no, because you're not between -1 and 1. You're not a cosine value, which means I cannot spit you out, and this overall expression is undefined. Inverse cosine of 10 is dead right there. Finally, tangent of inverse tangent of 10, that is 10. Because 10 asks tangent over here, hey, am I in your range? And tangent is very liberal. Tangent says, hey, every real number is in my range. So if you're any real number, I'll spit you out. And 10 does get spit out. Again, it's important that we have tangent here and inverse tangent inside here. If we had something like inverse sine or inverse cosine in there, then we use a different technique. Actually, inverse sine of 10 and inverse cosine of 10, you're dead meat. That would be undefined, and the whole thing would be undefined. If this were a value like 1/2, for example, then we might need a right triangle technique or something like that. Anyway, that's group 1. Next, we're going to look at group 2 for the inverse properties, a second set of inverse properties. So basically, what happens if the inverse trig function is on the outside and the regular trig function is in the inside? And of course, these are partners, inverse sine and sine, inverse cosine and cosine, inverse tangent and tangent. We're not mixing things up. We're not having, for example, inverse sine and cosine. Then we'll need a right triangle approach like in a later video.
Actually, the right triangle approach is more for group 1 than for group 2.
Okay, but let's say that theta is an angle. Now, when do we have these clean inverse properties? If you input theta, when can we get theta as our final output? If the inverse trig function is on the outside and the regular trig function is on the inside. Well, this angle theta is going to ask inverse sine. Again, it's going to ask the outer function, am I in your range or not? And if theta is in the range of this outer function, in this case inverse sine, then theta will be the output. It will be the answer. It's what this simplifies to. Well, what is the range for inverse sine? If you think of the unit circle, the range for inverse sine goes from -pi/2 down here up through positive pi over 2 up here. That's the range for the inverse sine function. So if theta is in that range for inverse sine, then theta gets spit out. Otherwise, what happens if theta is not in this range for inverse sine? Then one of several things could happen. If not in the range for arc sine, then what could happen? There are actually several possibilities. First of all, the answer could be a quadrantal angle, like pi or 3 pi over, well, actually, no. If theta is not in the range of the inverse trig function, what could happen? What are the possibilities? First of all, okay, the answer could be a quadrantal angle, although pi and 3 pi over 2 and 2 pi, those are not in the ranges of these inverse trig functions. The point is, what is the deal if theta is?
Well, no, pi is in the range of inverse cosine, just barely. One note.
For example, pi or 3 pi over 2, then the answer will be quadrantal. All right, so your answer could be quadrantal. For example, if theta is pi, sine of pi is 0, and the inverse sine of 0 is 0. 0 is not pi. The output is not the input. Again, if you put a pi in here, then the answer ends up being 0, and these are not equal. The answer is not theta, your input, but the answer is quadrantal. All right, that's one possibility. But what if you don't have a quadrantal angle? Then the answer could actually be a brother, or a co-reference angle, a brother or a co-reference angle, an angle with the same reference angle. So for example, if you input 5 pi over 6 in here, it turns out that the final answer ends up being pi over 6, which is a brother or co-reference angle that is in the range for inverse sine. Remember, the final answer for these, okay, will either be quadrantal, a brother or a co-reference angle, or undefined, or not real. Again, some examples. If the input is pi, the final output is 0, the answer is a quadrantal angle, but it's not theta, the input. If for theta, we have 5 pi over 6, and you can work this out. If theta is 5 pi over 6, the sine of 5 pi over 6 is 1/2. The inverse sine of 1/2, we're back to pi over 6 actually, which again is not theta, it's not the original input. I'll show you a shortcut later on. Undefined, well, that could happen in the tangent case down here, actually. Here, tangent actually has some restrictions, because if you try to plug in pi over 2 for tangent, tangent will have none of it. Tangent of pi over 2, you're dead right there. That's undefined. The whole thing blows up. So tangent is not so liberal in this case. All right, so again, if theta is in the range of the outside function, which is an inverse trig function, then you get theta if theta is in the range of the outside function. So in both group 1 and group 2, the inside argument is asking the outer function, am I in your range? If it is in the range of the outer function, then the input becomes the final output. It's perfect. It's a great inverse problem. It works cleanly. But if, here in this case, if theta is not in the range of that outer function, an inverse trig function, then the answer will not be theta itself. It'll either be some other quadrantal angle, some other brother or coreference angle, or the answer is undefined. All right. Back to these range issues. Theta asks inverse cosine here, am I in your range? Well, the range for inverse cosine is from 0 to pi. That's like the top half of the unit circle. If theta is in here, then theta is the output. For inverse tangent and tangent, theta asks inverse tangent, am I in your range? Now, inverse tangent is not so liberal as tangent and inverse tangent were back in group 1. Inverse tangent is not so liberal. See, the range for tangent is all reals. The range for inverse tangent is not all reals. It's only this interval. We don't even pick up the South Pole and the North Pole. We actually exclude the South Pole and the North Pole, but we do get everything in between. The range for inverse tangent is very similar to the range for inverse sine, except the range for inverse tangent is open. If theta is in this interval, then theta is spit out. For example, if theta is pi over 4 or pi over 6 or negative pi over 6, then that angle gets spit out in the end. But if theta is not in this interval, then the answer is something else. It could be a quadrantal angle, some other quadrantal angle. It could be some other brother or co-reference angle. Or, for example, if theta is pi over 2, the answer is undefined. We'll do some examples in the next video.
Okay, so yeah, group 2 is kind of disorienting, but this idea of looking at the range of the outer function. If you're in the range of the outer function, you're good to go. Questions, we'll do more examples. Questions. Let me sort of check the time here. We can do one more video and then we'll take a break. All right. Questions in chat.
Hi everyone, we're continuing with section 4.7 and we're going to do examples for group 2 of the inverse properties. Now for these, if the angle theta is looking over at this outer inverse trig function, and if we have a pair of partner inverse functions here, like inverse sine and sine, if theta is in the range of the outer function, in this case inverse sine, then theta will be the final output, the final answer, what this simplifies to. So you have to know the ranges for inverse sine, inverse cosine, and inverse tangent. Notice that the acute angles from 0 to pi over 2 are all in all of these ranges. So if theta is acute, then certainly theta is the final output. So for example, take here pi over 10. Pi over 10 is an acute angle, it gets spit out. Pi over 10 asks this outer function, inverse sine, am I in your range? And by the way, inverse sine and sine are corresponding inverse functions, they're partners. Pi over 10 asks the outer function, inverse sine, am I in your range? Inverse sine says, yes, you're between negative pi over 2 and pi over 2. Well, certainly you're acute. So the acute angles work for all three of these cases. I will spit you out, pi over 10. So this entire expression simplifies to pi over 10. I don't even care what the sign of pi over 10 is. It's an irrational number. As a decimal, it goes on forever and ever. The final answer is pi over 10. So if theta is any angle inside this interval, this range for inverse sine, then that value for theta is the final output. Now, if theta is not in the range of this outer function, then the result could either be some other quadrantal angle, some other brother or coreference angle, or undefined. But the answer will not be theta. If theta is not in the range of the outer function, then by definition of the range, this outer function is not allowed to spit out that value for theta. You're going to get one of these. Now, it's not so much that you have to remember these three possibilities if theta is not in the range. It could be just a matter of you working it out and you see what you get. So for example, let's consider the inverse sine of the sine of 5 pi over 6. The inverse sine of the sine of 5 pi over 6. Now, will this property up here in the upper left work for this value of theta? Well, 5 pi over 6, it's not acute, so I'm a little suspicious. 5 pi over 6 as this outer function, and by the way, inverse sine and sine are partner inverse functions. 5 pi over 6 asks this outer function, am I in your range? Inverse sine says, 5 pi over 6, well, that's not between negative pi over 2 and pi over 2. In fact, you're not even in the right quadrant. 5 pi over 6 is a quadrant 2 angle. And certainly quadrant 2 angles are not covered in the range for the inverse sine function, so I know that the answer will not be 5 pi over 6. So one way that you can work this out and get the correct angle is to just do it brute force. Do it step by step. What is the sine of 5 pi over 6? It's 1/2. The inverse sine of 1/2 is pi over 6. So you can go step by step and figure this all out. But there's a faster way of doing this. If you think that these steps might be a bit too tricky, there's a fast way of doing this. Consider the unit circle. Now, 5 pi over 6 is a quadrant 2 angle over here. And it does have a sine value, but the problem is that 5 pi over 6 is not in the range for the inverse sine function. Unlike the case for pi over 10. You see, for pi over 10 asks arc sine, am I in your range? Pi over 10 asks arc sine, am I in your range? And arc sine, inverse sine says yes, so pi over 10 gets spit out. But over here, in this example, 5 pi over 6 is not in the range of inverse sine. It turns out that, notice, the answer is a brother for 5 pi over 6. But which brother is it? We need a brother with two properties. We need a brother with two properties. We need a brother that has the same sine value as 5 pi over 6 does. Now, I hope that you know, or that you can figure out, that sine of 5 pi over 6 is 1/2. But just like it didn't matter what sine pi over 10 was numerically, it doesn't even matter what sine 5 pi over 6 is exactly. I hope you know it's 1/2, but you don't even have to know that for this example. You know the answer here is going to be a brother. 5 pi over 6 is not quadrantal. We don't think the answer will be quadrantal. And this will all work out. The answer will not be undefined. The answer is going to be some other brother or coreference angle. We want a brother or coreference angle with two properties. We want a brother with the same sine value that 5 pi over 6 does. It turns out that sine value is 1/2, but that doesn't even matter. We're going to use symmetry. We're going to use symmetry. Well, whatever the sine of 5 pi over 6 is, it's the y-coordinate of this point over here. What other point on the unit circle has the same y-coordinate? Over here. That y-coordinate is 1/2, but we don't even have to know that. I need a brother angle in quadrant 1. I need a brother angle in quadrant 1. But what brother do I want? We need a brother that is in the range of, in this case, the inverse sine or arc sine function. What's the range for inverse sine or arc sine? From negative pi over 2 to pi over 2. And what is the only angle in this range that's a brother to 5 pi over 6? The final answer is pi over 6. And that is our final answer. It's the only brother for 5 pi over 6 that has the same sine value. We want a quadrant 1 angle, not a quadrant 4 angle. And it's in the range for the inverse sine function. It helps that pi over 6 is acute. Because we know that the sine value has to be positive, we know that the final answer is going to end up being acute, since this is not quadrantal. All right. So you could either work this out brute force. Sine of 5 pi over 6 is 1/2. The inverse sine of 1/2 is pi over 6. Or just use symmetry. You need a brother with the same sine value, in particular, the same sign, SIGN for the sine value, positive as opposed to negative in this case, and it's got to be in the range for the inverse sine function. All right.
Okay. All right. Well, now's a good time for a
Hi,
break,
everyone.
actually.
We've been looking.
All right. Okay. So then we'll take a 10-minute break, and we'll continue on with talking about how to simplify these expressions algebraically. What happens if we mix them up a bit? All right. So let's go ahead and take a 10-minute break. I have 8:16. We'll come back at 8:27. All right. So back at 8:27. Please remember to mute. All right, and I'll come back and record, and I'll see you in 10. All right. Okay, so I am recording. I'm trying to mute it before I try to keep it muted so that that loud voice doesn't hurt your computer. All right, so we're back. Any questions in the chat? Before we go on, any questions in the chat? All right. So we're proceeding with inverse trig functions, and we're going to talk about what happens when we get kind of mixes there, and we get right triangles. All right, so starting now. Okay, any questions in chat? Starting now.
At two groups of inverse. Hi, everyone. We've been looking at two groups of inverse properties for trig functions and their inverses. In many situations, trig functions and their corresponding inverse functions undo each other. For example, sine of inverse sine, or arcsine of x, equals x if x, this inner argument, is in the range of the outside function, in this case sine. The range is this closed interval from -1 to 1. Under these circumstances, if x is the input, then x is the final output. We simplify this expression as just x under these circumstances. But what if instead of inverse sine, we had another inverse trig function, like inverse cosine or inverse tangent? Then we wouldn't have an inverse property. In order to simplify the expression, we may have to use right triangles. We're now going to use a right triangle method to rewrite an expression like this as an equivalent algebraic expression in x, something that we might have seen in chapters 0, 1, or 2. Think of the quadratic formula. So cotangent and inverse cosine will not undo each other. If the argument were a cosine value, like 1, for example, then you could just work this out. But what if the argument is variable, like x over 3? Then the right triangle method can be used to simplify this more generally. All right, we're going to use substitution. Remember that the output for an inverse trig function can often be thought of as an angle. Let's call it theta. We're going to let theta be the inverse cosine of x over 3, the entire argument for cotangent here. Again, we relate the outputs of inverse trig functions to angles, often. So we want to simplify cotangent of theta. Cotangent of theta, where theta is this inverse trig expression over here. Now, if theta is inverse cosine of x over 3, what can we say as a result? Well, we can say that the cosine of theta is x over 3. Let's write it like this. So we're going to rewrite this as inverse cosine of x over 3 equals theta. I'm using theta because we can think of this as an angle. If you want to use u, for example, that's fine. Well, if inverse cosine of x over 3 is theta, then as a consequence, cosine of theta has to be x over 3. How do you invert this statement? If inverse cosine of x over 3 is theta, then cosine of theta has to be x over 3. It's like a zigzag. Cosine of theta has to be x over 3. By the way, we're going to assume that x will not cause any domain problems. So x, for example, could not be a number greater than 3. All right, cosine of theta equals x over 3. Now, we can use SOHCAHTOA and develop a right triangle model. SOHCAHTOA. We're going to set up a right triangle model so that cosine of theta is x over 3. Let's make this angle measure theta. SOHCAHTOA. Cosine is adjacent over hypotenuse. And you can see that if you set up this right triangle model, then it's true that cosine of theta will be x over 3. Cosine of theta is adjacent over hypotenuse. And then, since we want to find the cotangent of this angle, remember, we want to simplify cotangent of theta over here, then it would help to find an expression for b, the length of this leg here in terms of x. I'm calling it b here. You could call it a or something else. It turns out to be the square root of 9 minus x squared. And how do we get that? Well, what theorem will relate these three expressions for the sides of this right triangle? The Pythagorean Theorem. X squared plus b squared equals 3 squared. X squared plus b squared equals 9. Again, people might be tempted to isolate x squared or b squared on one side because they feel like it, but no, it's not that easy. X squared plus b squared equals 9. And we ultimately want to solve for b, which is buried in there. Sorry, but you're going to have to do some algebra. X squared plus b squared equals 9. First, let's isolate the b squared term. We accomplish that by subtracting x squared from both sides. On the left side, when you subtract x squared, you're left with b squared. On the right side, 9 minus x squared results on the right side. We're subtracting x squared from both sides. Now from the square root method, b can be plus or minus the square root of 9 minus x squared. And then when applying this method, it turns out that we can delete the plus minus symbol. You can analyze various cases to see why that's true. Here, we assume that theta was acute for our right triangle model, but it turns out that our right triangle model will work even if theta is not acute. We take b equals the non-negative root of 9 minus x squared. And we can label the side like so. Remember, to find cotangent of theta, it's going to be helpful to find an expression for this side length in terms of x. Again, what do we want? Cotangent of this angle theta. Now, it might be helpful to consider its reciprocal function first. What is tangent of theta? Tangent of theta, TOA, in SOHCAHTOA, tangent of theta is opposite over adjacent. Tangent of theta is b over x, or the square root of 9 minus x squared over x. That's tangent of theta. But then, to get cotangent of theta, we have to take the reciprocal. Cotangent of theta is then x over the square root of 9 minus x squared. Cotangent of theta is x over the square root of 9 minus x squared. And we're done there. This is an algebraic expression in x. It's something we might have seen in chapters 0, 1, or 2. Think of the quadratic formula. We're allowed to have things like exponents, nice roots, things like that. Now here, a lot of students would try to rationalize the denominator. Actually, I don't recommend that. Generally speaking, this expression here would be considered simplified. If the radicand down here is variable, we actually tend not to try to rationalize the denominator. For example, if x is a messed up number, like the 5th root of 2 or something like that, then we would not be able to rationalize it easily anyway. Not easily. What if x is something like 1 over e? It's basically impossible. All right, so this is our simplified algebraic expression. By the way, the square root of 9 minus x squared is not 3 minus x. We do not take square roots term by term. So please do not try to simplify this to 3 minus x. Now I claim that this is our expression for cotangent of theta. It's a simplified algebraic version of cotangent of theta, where theta was all this inside here. So my claim is that this expression I have in blue here is equivalent to x over the square root of 9 minus x squared, as long as we don't have any domain problems. Well, let's verify this on Desmos. The original expression is here. Let's graph y equals cotangent of arc cosine or inverse cosine of x over 3. I'll turn that graph on, and it's this red graph over here. It turns out to have VAs, vertical asymptotes, at x equals -3 and x equals +3. That makes sense because if you look here, we know that we're going to be in trouble if x is something like 4, 5, or 6, then x over 3 would not be a cosine value. Likewise, if x were like -4, -5, or -6. Even if x is 3, for example, then we'd get inverse cosine of 1. Inverse cosine of 1 is 0, and it turns out cotangent of 0 is undefined. That corresponds to the VA at x equals 3. Likewise, at x equals -3, we also have a VA. It turns out that the domain for this expression, this function, is going to be the open interval from -3 to +3. Well, guess what? Look at this expression that we're claiming is equivalent to the given expression here. X over the square root of 9 minus x squared. Using the methods from chapter 2, section 2.7, the domain for this expression or function is, again, the open interval from -3 to 3. Notice that at x equals +3 or -3, we're going to end up with a 0 denominator. That corresponds to the VAs at x equals -3 and x equals +3. Again, my overall claim is that this expression, this algebraic expression, is equivalent to the given trig and inverse trig expression. Let's turn on the corresponding graph and see if this red graph just recolors. Yes, it does. The purple graph is the same as the red graph. You can see this flashing, which means that these equations are equivalent and these expressions on the right sides are equivalent. This is not a proof, but it's a very convincing and gratifying check. The fact that these two graphs are the same. Now, I'm not just playing with you. You're actually going to have to work out and simplify expressions like these in your Calc 2 class, Math 151. Because in Math 151, there's a technique called integration using trigonometric substitutions, where you actually have an integral problem and you want to use a trig sub like cosine of theta equals x over 3. And at some point, you have to unravel an expression like this and rewrite it algebraically. You actually do that in a Calc 2 class. So you will see this later on in your calculus adventures. Next up, we're going to talk about how to use inverse trig functions to solve equations.
So this is an example of something that you're going to see 2 semesters from now. So it's kind of like genetics. Sometimes, a gene expresses itself a couple generations down the line. pre-calc is not just pre-calc 1, it's also pre-calc 2. Right. Any questions? Any questions? All right. Simplifying these inverse trig and trig functions algebraically. These nice expressions over here.
Next time.
It's because of the Pythagorean relationships.
Hi, everyone. We're going to go back to sections 4.2 to 4.4 and do some of the parts we skipped earlier. In part F, we're going to talk about how we can use inverse trig functions to solve an equation like this. Sine of theta equals 0.4. Now, I need to make a point first, and I'm going to go all the way back to factoring from section 2.5. So in section 2.5, let's say that you run into your old algebra teacher in a dark alleyway, and your old algebra teacher asks you to factor x squared minus 3. Now, you should ask your algebra teacher over what set? And then maybe your algebra teacher will dissolve and disappear, because the answer will differ depending on what set of coefficients will be legal. If you try to factor this old school over the integers, like you may have tried to do in your old algebra class, guess what? X squared minus 3 is prime over the integers. You cannot break this down any further if you're only allowed to use integer coefficients. But if you're allowed to use the whole swath of real coefficients, if you're factoring this over R, the set of real numbers, this does break down. You can think of this as a difference of two squares, and this factors as, remember, x plus root 3 and x minus root 3. So you see, the answer to this factoring problem depends on what set you're allowed to factor this over. What are the coefficients that you're allowed to use? Well, likewise, when we asked, how do you solve sine of theta equals 0.4? You need to ask on what interval. On homework or exams, I hope to make that clear. Now, in general, if you're asked this on a general test, then we assume that you want all real solutions. But for now, let's be careful about the interval of values for theta that we're really looking at. So you want to ask on what interval. Solve this equation on what interval. That is, on what interval of values for theta. These potential solutions for theta. Okay, first off, let's solve this trig equation on the open interval from 0 to pi over 2. In other words, we're going to find the acute solution or value of theta that will make this work. What is the only acute angle in radian measure such that sine of theta equals 0.4? There's going to be one acute solution here. Remember, your answer to a solve an equation problem is a solution set, and I claim that you will only get one acute solution. We will have a solution because 0.4 is a legitimate sine value. It's in the range. If we had a 2 or a 3 here, then the solution set would be empty. But here we will have one acute solution. Well, let's look at the unit circle. Let's look at the unit circle. All right. On the unit circle, remember that sine of theta corresponds to y. Sine of theta corresponds to the y coordinate on the unit circle. Now, where on the unit circle is the y coordinate, the sine value, equal to 0.4? Let's say over here and over here. So in general, there will be solutions to this in quadrants 1 and 2. But wait, we only care about solutions in this narrow interval. We only want the sole acute solution to this equation. So we only want the acute angle, the acute representative for this point over here. Sine of theta equals 0.4 has only one acute solution. This angle. We want this measure for theta. And how would you calculate this on your calculator? How would you find the measure for this acute angle? Well, it depends if you're in degree mode or radian mode. Make sure you're aware of what mode you're in and how to go back and forth between the modes. But it turns out that if you're in degree mode, when you work out the inverse sine of 0.4, and that's what you have to calculate, the inverse sine of 0.4. We have to calculate the inverse sine of 0.4. The inverse sine or arcsine of 0.4, which we know will be an acute angle. Now in degree mode, we're going to get 23.6 degrees. In radian mode, you're going to get 0.412 radians. Now let's check to see that this makes sense. So I'm claiming that over here, the corresponding angle will be about 23.6 degrees or about 0.412 radians. And remember that the y-coordinate, the sine value, is 0.4. Well, it makes sense that the angle here is less than 30 degrees because for 30 degrees, I'll put that in purple, for 30 degrees, this might be a bit too steep for 30 degrees in reality, but for 30 degrees, remember that the sine of 30 degrees is 1/2 or 0.5. I hope you remember that. The sine of 30 degrees is 0.5. Well, if the sine of 30 degrees is 0.5, if this is 0.5 up here, I know it's not to scale. If the sine of 30 degrees is 0.5, it makes sense that the sine of a smaller angle, in this case about 23.6 degrees, will be 0.4. And 0.412 radians will be a bit less than pi over 6 radians, which was 30 degrees. Okay, so this answer makes sense. If you're asked to find the acute solution for this equation, remember the answer to a solve an equation problem is a solution set. There's only one solution that's acute, and it's about 0.412 radians. I'm going to use radian measure here. Although when answering a problem, make sure that you're answering using the appropriate unit, whether it's degrees or radians. What is it you're asked for? The hard part is not going between degrees and radians. The hard part is knowing what to do. How many solutions do you have, and where are they? So this equation only had one acute solution. But now, let's ask a second related problem. What are the solutions to this equation on this interval, basically between 0 and 2 pi? That is, find the solutions, values for theta, around one classic revolution around the unit circle. I have a parenthesis here because, remember, 2 pi is coterminal with 0. All right. So let's see what happens there. Between 0 and 2 pi. So this time, we're going all around the world once. In terms of looking for solutions, we're going to look around the unit circle in terms of looking for solutions. From 0 to 2 pi. What are the solution values for theta we pick up? All right. Now again, we want to find angles whose sine value is 0.4. And actually, I can appeal to this picture back here. Again, we're looking for 2 points whose y-coordinate is 0.4. I should probably lower this a bit. 2 points whose y-coordinate is 0.4. All right. So between 0 and 2 pi, how many angles are we going to pick up? as we go around the world, as we go from 0 all the way around to 2 pi, not quite 2 pi, what angles do we pick up? Well, we pick up the same acute angle that we did before, the whole 23.6 degrees or 0.412 radians. In fact, I can copy this. So we get this acute angle over here, but wait, we also have this supplementary angle over here. It's a brother, a coreference angle. They have the same reference angle, namely this. Now, how can we get a measure for this supplementary angle in quadrant 2? Well, in degree mode, you would do half a revolution, 180 degrees, minus the reference angle, which was the 23.6 degrees. So the supplementary brother in quadrant 2 that we want will be about 180 degrees minus 23.6 degrees. That's about 156.4 degrees. So in degrees, that's going to be this degree measure for this solution. In radian measure, you use pi radians. Instead of 180 degrees, you use pi radians to represent the half revolution. Pi minus 0.412 is about 2.730 radians. So again, in quadrant 2, the solution that we want will be about 156.4 degrees, or about 2.730 radians. I have the right to put that 0, so I'll put it in. I'm going to put these out to 3 decimal places. All right. So in radian measure, our 2 solutions will be about 0.412 radians and about 2.730 radians, this quadrant 2 angle, which is still between 0 and 2 pi. It's obtuse. So in solution set form, if we want the solutions between 0 and 2 pi, there are 2 of them. One is about 0.412 radians, that's the acute quadrant 1 solution, and one is about 2.730 radians. That's the obtuse quadrant 2 solution. And this kind of analysis will help you on the homework. It's harder when this value over here is negative. Then you really have to think. When in doubt, think about the reference angle. So even if the reference angle itself is not a solution, it's still a good thing to build things off of, because it's easy to get from the reference angle to key brothers in the other quadrants, whether you're in degree mode or radian mode. Now here's a preview of chapter 5, namely section 5.3. Solve sine of theta equals 0.4 on R, the set of all real numbers. Let's find all real solutions. That's going to be a chapter 5 problem. So what do we pick up? Well, as we go around the world, we pick up our 2 solutions from before, from question 2, but we're allowed to go around and around and around and around, both counterclockwise and clockwise. So we want not just these 2 solutions, but all of their coterminal twins. So we want this, also this, plus 2 pi, plus 4 pi, and so forth. Also minus 2 pi, minus 4 pi, and so forth. We want this obtuse solution, and also this guy plus 2 pi, plus 4 pi, and so forth, and minus 2 pi, minus 4 pi, and so forth. So we can take these guys and add or subtract integer multiples of 2 pi. This is how we'll write our approximate solution set in chapter 5. It's this long thing. The solution set is the set of all theta in the reals such that theta is about 0.412 plus 2 pi n, where n is integer, or theta is about 2.730 plus 2 pi n, where n is integer. Again, we want this acute solution and also all the coterminal twins. N can be negative as well, a negative integer. Also, we want 2.730, this obtuse solution, and also its coterminal twins, where n could be 0, a positive integer, or a negative integer. So in chapter 5, and specifically in section 5.3, we're going to solve trig equations on R, and we're going to get all real solutions. Typically, we'll get infinitely many solutions. Sometimes, like for sine of theta equals 2 or 3, we'll get the empty set. You'll get lots of practice on the homework. So that's section 4.7, including a rollback to 4.2 to 4.4. Next, we'll discuss word problems.
So we're looking back, and also I mentioned that on Thursday, I'm going to start 5.3 on solving trig equations, and actually that piece of 5.3 I'm going to start with, that's going to be relevant to this stuff. So I'm looking back to the earlier parts of chapter 4, and I'm looking towards Thursday when a piece of chapter 5 will help a lot with this stuff, okay, even though it's chapter 4 homework. All right, any questions? Any questions?
Hi, everyone. Let's do a word problem. We're still in the 4.2 to 4.4 block. This is the last part there. Part G, a word problem. So for example, a 6-foot-tall man like me, shut up, standing on a flat surface. So it's good to draw a picture. That's a key trick for these problems, drawing a picture. So a 6-foot-tall man, right? The 6 feet is here and also over here. And these are in feet, by the way. Standing on a flat surface, as opposed to an incline. So word problems, sometimes it's tricky to state them precisely. So this man is standing on a flat surface, not a hill. And he's looking up at a 20-degree angle of elevation. Now, I'm kind of assuming that his eyes are on the very top of his head, so we're kind of ignoring the forehead. But he's looking up at a 20-degree angle of elevation, okay, up towards the top of a flagpole. So here's our flag being patriotic, right? Okay. Well, our flagpole's here, right? Our flagpole is over here. His feet are 70 feet away from the base of the pole. By the way, if you want to put a unit, that crit mark can stand for feet. Okay, let's see. His feet are 70 feet away from the base of the pole. And we have a right angle here because, again, it's a flat surface, not a hill. How tall is the flagpole? And we're going to denote the height of the pole by x. And that's going to be in feet. Now, sometimes the answer is not going to be x. For example, when we set up this right triangle problem, some people might want x to be the actual side of the right triangle here, and then the answer would be x plus 6 in feet. But the way I'm setting it up, x will represent the answer in feet. Okay, now, the man is 6 feet tall. So we have this rectangle down here that's 70 feet by 6 feet. And on top of the rectangle, there's a triangle. Now, the overall height of the pole is x in feet. We have 6 feet corresponding to this height, this line segment. So this side of the triangle is given by x minus 6 in feet. And we're going to use that as part of SOHCAHTOA. X minus 6 is the length of this leg for the right triangle. Okay, so we ultimately want to solve for x. We have an angle. We have the adjacent side, it's 70 feet. We want to know about the opposite side. So what trig function relates an angle, the opposite side, and the adjacent side? It sounds like TOA, SOHCAHTOA. Sounds like a tangent problem. All right, tangent of 20 degrees is opposite over adjacent. X minus 6 in feet, so x minus 6 in feet over 70 feet, which means that the feet units will cancel out. The top is in feet, the bottom is in feet. Tangent of 20 degrees has no unit. It's a strict ratio. Tangent of 20 degrees is x minus 6 all over 70. We want to solve for x. First, let's get rid of the 70 on the right side. We're going to multiply both sides by 70. Time for some algebra. 70 times tangent of 20 degrees equals x minus 6. And then to solve for x itself, we're going to add 6 to both sides, 6 feet. So, and now I'll turn it around. X equals 6 plus 70 times tangent of 20 degrees. 6 is in feet, 70 is in feet. Tangent of 20 degrees has no unit. X will be in feet. Now be careful, don't add 6 and 70. We do not get 76 here. a scientific calculator should know that the product comes first. And make sure your calculator is in the appropriate mode, degree mode. 20 is in degrees. So make sure you're in degree mode. We get to the nearest tenth of a foot, about 31.5, and we should put a unit, feet, because these were in feet. It's a consistent unit. Nowadays, more and more, it's good to write down the final answer using proper English sentences. The flagpole is about 31.5 feet tall. Okay, that was the question. What is the height of the flagpole? It's about 31.5 feet tall. All right. Once again, if instead, I'll put this in purple. If instead the height of this triangle were x in feet, then the height of the pole would be what? X feet plus 6 feet, well, that's going to be x plus 6 in feet. Which means if you were to make the height of this triangle x, then your answer, the height of the flagpole, would require you to add 6 feet. So make sure that you get the height of the flagpole. Your final answer may not be x. If you make this x, your answer will be x plus 6 in feet. But we set it up here so that x is the height of the pole. The flagpole is about 31.5 feet tall. Again, remember the units in your final answer. And try to avoid approximating until the very end. Many people are tempted to round off things right in the middle, but then you're in danger of losing accuracy. It is good to try to keep things as exact as possible along the way, like we did for logs back in chapter 3. If you do round off, make sure you use many significant digits just to be safe. Okay, in section 4.8, I discussed some general principles for word problems, but really you have to practice them. In fact, when you actually practice these word problems, the hardest part for many students is figuring out which side is which length. So they're doing a word problem and students aren't sure. Well, is this value this leg? Is it this leg? Or is it the hypotenuse? And that depends on the word problem. That's hard to teach. You get it from practice. But what are some general principles for word problems? First of all, well, read the problem carefully and highlight as appropriate, underline or highlight, in case you have to keep going back to some information. Define variables, like you might say, let x be the height of the flagpole. Draw a diagram and label them. Sometimes that's a decent substitute for this, but technically you should always define your variables, preferably in words. But diagrams help a whole lot. If anything, the diagram is more useful to a student. In calculus, by the way, you'll need to keep track of which aspects of the problem stay fixed or constant and which aspects change. For example, in ladder problems, let's say we have a ladder leaning up against a wall, and it's on the flat ground here. The length of the ladder tends to stay constant, but this leg here and this leg here can vary as the ladder slides around. So in calculus, you have to keep track of what stays constant and what changes. Y and X could be changing, but this could be a constant, like 15 feet. Make appropriate unit conversions where appropriate. So for example, if Y here is in inches and X here is in feet, then you have to convert from one to the other. They both have to be in inches or they both have to be in feet. It's one or the other. They have to be consistent. They can both be in inches or they can both be in feet or even some other unit, as long as you're consistent. So make sure you get to one unit. Sometimes the problem will give you red herrings, numbers that don't really matter. For example, if I say in the year 2020, this happens, you probably won't need the 2020. So ignore red herrings. They're there to trick you. Make sure you clearly answer all the questions you are asked. Answer all the questions you are asked. Okay? And sometimes X does not represent the final answer. So for example, in our flagpole problem, if X is just the length of this leg, then X plus 6 in feet is the height of the pole. That's what you would really want. Sometimes X is not your final answer. Now, in a math class, you're expected to give exact answers, but in word problems, you might be asked to round them off. So be aware of what the question is asking for. So again, in math class, we expect exact answers, but in word problems, we're often asked to approximate or round off and follow the instructions in the word problem. If you do round off, use many sig figs just to be careful. In your final answer, write units where appropriate, like feet in our example. And in fact, we tend to prefer complete sentences nowadays. See if your answer makes sense. So if I claim here that this flagpole is 1,000,000 miles high, you probably made an error. I would bet that you made a conversion error. For example, maybe you should have converted from inches to feet or vice versa, and you didn't do that. Again, be prepared to write your final conclusions using plain English sentences. In these days of Common Core, we tend to prefer that. Okay, so those are some principles of word problems, but the bottom line is you have to practice them. I'm going to discuss techniques that are specific to right triangles in the next video.
Okay, so before it's more of the art, right? This is kind of the art of setting up a solution to a word problem, which is an art you develop with practice. Next is more sort of traditional SOHCAHTOA type stuff.
Hi, everyone. We're going to solve right triangles. So you could say that a triangle consists of 6 parts, 3 angles. For a right triangle, one of them is a right angle, and 2 complementary angles that add up to 90 degrees. And also 3 side lengths, which we could label little a, little b, and little c for the hypotenuse. When we solve a right triangle, we're given some of these parts, and we have to find all the others. In a word problem, you might just want to find one of these parts in the end. Now, what will relate these various parts? Well, we have 3 tools that we can use. What relates the 3 side lengths of a right triangle, A, B, and C? Well, a squared plus b squared equals c squared. That's Pythagorean Theorem. That relates the side lengths. Pythagorean Theorem. What relates the angles? Well, the interior angles for any triangle, not just a right triangle, must add up to 180 degrees. So that's a rule for the angles. And what will relate side lengths and angle measures, sides and angles? SOHCAHTOA. For example, sine of theta is opposite over hypotenuse, and so forth. That relates angles and sides. So this 180-degree sum rule for angles, the Pythagorean Theorem for the side lengths, and SOHCAHTOA, which relates angles and side lengths, these are 3 key categories of tools that we're going to use. For example, let's solve the triangle below. I'm giving you that we have a right angle here. This leg is 7 feet, and the hypotenuse is 9 feet. And by the way, this is the conventional way to label a right triangle. Capital A and capital B represent the acute angles, or their measures. Angle C is the right angle. And then the side lengths are labeled little a, little b, and little c. The side with length little a faces or is opposite to angle big A, and so forth. Little b is opposite to big B, little c is opposite to big C, the right angle. So little c is the hypotenuse. This is a conventional way of labeling a right triangle. By the way, convert units as necessary. If, for example, I had given you 84 inches for the length of A, you may want to convert to feet. You'd have to make the units consistent. All right. Now, first of all, I'm giving you the right angle here and 2 side lengths. Now, what's missing? What do we need to find? We need to find the length of little b, and we need to find the measures of angle A and angle big B. I'll double circle these. We need these two angles and this side length. Okay. Now, again, given these two side lengths, how can we find this missing side length on a right triangle? The Pythagorean theorem. A squared plus b squared equals c squared. I'll do the calculations over here. All right, a squared plus b squared equals c squared. So, and these are consistent units, feet. 7 squared plus b squared equals 9 squared. 40, and now, bear in mind, the b or b squared is buried in there. Don't engage in wishful thinking and isolate b squared immediately. You'll probably make a mistake that way. The b squared is buried in there. Let's isolate the b squared. We do that by subtracting the 49 from both sides. Remember, 7 squared is 49 and 9 squared is 81. 49 plus b squared equals 81. Let's subtract 49 from both sides. B squared equals 81 minus 49 is 32. Square root method, b equals plus or minus the square root of 32. But because we have here a right triangle, we have no funky things going on with quadrants, we take the positive length. So we take b equals positive root 32. Let's simplify that. The largest square that divides 32 nicely, the largest perfect square, is 16. And the 16 pops out as a 4. Root 32 is root 16 times root 2. Root 16 is 4. So b is exactly 4 times the square root of 2 in feet. So b will be 4 root 2 in feet. 4 root 2, by the way, if you approximate this on a calculator, well, root 2 is about 1.4, so I know that this will be about 5.6 feet. All right. Now, we now have all 3 side lengths for this right triangle, and we know that big C is a right angle. How can we find these 2 other complementary angle measures? For example, what if we want the measure for angle A? Well, let's see now. At the beginning, I was given that the opposite side was 7 feet. That's the opposite side relative to angle A. And the hypotenuse for the triangle was 9 feet. At this point, I could even use the fact that the adjacent side is 4 root 2 feet, but we might want to avoid that, especially if you're rounding off. So what trig function will relate an angle, the opposite side, and the hypotenuse? That sounds like the sine function. Sine of A equals opposite over hypotenuse, 7 feet over 9 feet, or just 7/9. Sine of A equals 7/9, and I know that A has to be an acute angle. So A itself has to be the inverse sine of 7/9. I'm sure we'll want to round that off. In degrees, it's about 51 degrees. And for these applied problems, when we're solving a right triangle, for example, we tend to use degrees. A is about 51 degrees. It's the acute angle whose sine value is 7/9. So this here is going to be about 51 degrees. Now for angle B, we could use SOHCAHTOA again, but let's do something even easier. Remember, the 2 acute angles of a right triangle are complementary. We're basically using the 180 rule for triangles in general. 90 degrees will be taken up by angle C. So angle A and angle B have to add up to 90 degrees. They're complementary. So we subtract 51 degrees and 90 degrees from 180 degrees, or just subtract 51 degrees from 90 degrees. Either way, remember angle B is the complement of angle A. Either way, angle B will have measure about 39 degrees. Be careful because many students might say 49 degrees because they might think percent. It's true that 51% plus 49% is 100%, but we're thinking degrees here. 51 degrees plus 39 degrees is 90 degrees. So be careful. We want these to add up to 90 degrees, not 100 degrees. You're thinking 100% then. Okay, so this here, angle B is 39 degrees to the nearest degree. So this all makes sense. These all add up to 180 degrees. The interior angles all add up to 180 degrees. And check this out. The eating rule checks out. I call this the eating rule. The idea being that larger angles eat or face longer sides. The largest angle here is the right angle, 90 degrees. The right angle must be the largest angle in a triangle. It faces the hypotenuse, the longest side, 9 feet. The medium angle here is 51 degrees. It faces the medium side, 7 feet. The smallest angle, 39 degrees, faces the shortest side, which turns out to be about 5.6 feet. If you had gotten something like 10 feet or 56 feet, you know you made a mistake. Also, there is something called the triangle inequality. Which basically says that a detour cannot be shorter than a straight length. So for example, 9 feet has to be shorter than 7 feet plus 5.6 feet because this represents the straight line segment distance. The detour here must be longer. So you must satisfy the triangle inequality. So again, this could not be 56 feet. So if you accidentally put the decimal point over here, you know this cannot be 56 feet because 9 feet plus 7 feet gives you a shorter detour, 16 feet. That cannot happen. So these are some basic checks. They're not necessary, but they're basic checks just to make sure that your answer makes common sense. It's good to check to make sure your answer makes common sense. So we've solved this right triangle. We now have all 3 angle measures and all 3 side lengths. Part C is optional. These are other ways that you can measure angles or directions. So for example, if you're going in this direction, you might say that a boat, say, is going 30 degrees east of north. So this ray here makes a 30-degree angle with due north. Again, that will not be on the homework or exams. In air navigation, you might take due north as 0 degrees and measure clockwise. So this southeasterly direction may correspond to, say, 150 degrees clockwise from due north. But again, Part C will not be on homework or exams. And that is Chapter 4.
And it's about time we have a fun video. I haven't had that in a while, but I have a great one here. Okay, I have a great video for you. Basically, we're going to start Analytic Trig on Chapter 5, which combines algebra and trigonometry, right? 2 of the great subjects in math. So we're going to mix algebra and trigonometry. So here's my little video for that. I hate how loud Zoom is when you start and stop recording. That's the only thing, right?
Hi, everyone. We're going to start Chapter 5 on Analytic Trigonometry. We're going to marry our 2 favorite subjects, algebra and trig. In Section 5.1, we're going to review and apply the fundamental trig identities. There were 5 basic categories, 5 categories of identities that we looked at in Chapter 4. The reciprocal identities. For example, what's the reciprocal of sine of x? It's cosecant of x, not secant of x. Make sure not to mix these up. And you need to know these identities left to right and right to left. The quotient identities, where we expressed tangent of x and cotangent of x in terms of sine of x and cosine of x. The Pythagorean identities, these three identities that involved the squares of the 6 basic trig functions. Sine squared of x plus cosine squared of x equals 1. We can divide by sine squared of x on both sides to get the second identity, and divide by cosine squared of x to get the third identity.
By the way, one note. So this is part of my 5.1 notes. It's like on an early page in chapter 5. This will help in chapter 4. So you might want to use bits of chapter 5 when you're doing chapter 4. This is a handout thing I showed you early on, right?
Some ways to remember these. Remember that the up u, down u guys squared are all alone on the right side. And also on the second identity, remember that these co-guys go together. That's one advantage to having the reciprocal of sine of x be cosecant of x. The cofunction identities, there were many of these. Bottom line, cofunctions of complementary angles are equal. And the even odd or negative angle identities. Remember that cosine is even, and so is its reciprocal function secant, meaning that these -1 factors on the arguments here, they can die. Cosine of opposite x equals cosine of x, same for secant. But for the other 4 basic trig functions, they're odd. So these negative signs basically pop out. These -1 factors on the arguments basically pop out and can become coefficients. So we need to remember and be able to apply these identities. Now, what do we mean by simplifying? Well, basically, we want to make these expressions more compact. So, for example, we'd want to replace 1 over sine of x with cosecant of x. There is no golden book for simplifying, but generally speaking, we want to make expressions more compact. Follow the conventions on the notes and the homework. You'll get used to it. So, how can we simplify trig expressions? There are many strategies. One strategy is to break things down into sine and cosine, kind of like taking change. If you're doing change, maybe you want to break things down to pennies and nickels. Sine and cosine, that's like pennies and nickels. And then we might be able to combine things and build things up. All right, let's simplify sine to the 4th x times cotangent to the 4th x. Well, let's see. We can break apart cotangent of x. By the quotient identities, cotangent of x is cosine of x over sine of x. So by the rules of exponents, it's true that cotangent to the 4th x is equal to cosine to the 4th x over sine to the 4th x. This does work. The exponent is shared on the top and the bottom. So when we replace cotangent to the 4th x by that fraction, what happens? Look here. Sine to the 4th x divided by itself is 1. Let's put little ones here. That's a good habit. And the result is cosine to the 4th x, which is simplified. So for example, if we wanted to know the value of this when x is pi over 3, instead we can just plug in pi over 3 here. Cosine of pi over 3 is 1/2. The 4th power of 1/2 is 1/16, which is the value of this expression at pi over 3. But be careful. Actually, this expression does not hold for 0, pi, 2 pi, and so forth, because remember, there's a hidden restriction here. Sine of x, when that's 0, the expression up here is undefined. And in fact, we're supposed to have this restriction here. Sine of x cannot be 0. So if you wanted to be totally precise, we should make a note that sine of x is not 0. Admittedly, in chapter 5, we sometimes get a bit sloppy when it comes to matter of domains and hidden restrictions. But actually, if x equals 0, the expression here is undefined. The answer is not 1, which is what would happen if you try to plug in 0 here. But basically, for values of x that do not make sine of x equal to 0, the expression up here will be equivalent to the expression over here. And we can use Desmos to help check that for us. Let's graph y equals this, and then y equals this. So on Desmos, we have here y equals sine to the fourth x. It turns out that you need to type it in like this. Desmos will not accept sine to the fourth. You need to type it in as the fourth power of sine of x, times you would type out cotangent to the fourth x as the fourth power of cotangent of x. What's the graph? It's this. Although, as I mentioned before, this function or expression here is undefined whenever sine of x is 0. For example, when x is 0, pi, 2 pi, and so forth, the integer multiples of pi. Technically, we're supposed to have holes here. For example, at 0, 1, there's supposed to be a hole. But Desmos does not admit that unless you actually try to click on the point there. And then Desmos notes, hey, wait a minute. There's a hole here at 0, 1. There's a hole here at pi, 1. Can we get that? Maybe not. So Desmos is not so good at identifying holes. But there are technically holes at x equals integer multiples of pi. Again, this will not be a key stress in this chapter. What happens if we graph y equals cosine to the fourth of x? Y equals cosine to the fourth x. We get the same graph. Let's flash it. We get the same graph. Not a proof, but this is very gratifying. It makes us feel very confident that these two expressions are equivalent aside from the hidden restriction issue. The graph of this does not have any holes on it. The graph of this does have holes. So to make these truly equivalent, you need to put in that restriction that we do not allow values of x that make sine of x equal to 0. But basically, these two expressions are equivalent. That helps a lot. For example, if you want to take derivatives or integrals in calculus, you'd rather work with this guy than with this guy over here. So simplification is your friend, very often in calculus. We'll discuss other techniques for simplifying later on.
Okay, so I just wanted to take a little bite out of chapter 5 today. We'll talk about more techniques like factoring on Thursday. And again, as we look at this algebraic approach to trig, I think that's going to help you master trig more. So even though you may be working on the chapter 4 homework, of course, as always, I strongly encourage you to come on Thursday. And actually, what we discuss on Thursday, especially with basic trig equations in 5.3, that will help you with some chapter 4 problems, I'm telling you. So certainly come on Thursday, not just for the chapter 5-6 homework later on, but even for your chapter 4 homework. What we do on Thursday will help you with your chapter 4 homework, all right? Okay, so it's been a good day. I have 9:20, hey, well, it's 9:30. Okay, I have 9:30 right now, all right. So that's our class, but as always, I'm willing to stay for questions. I know at least one student, if not more, will have questions, all right? So again, the homework for this is due in 8 days, right? And I'm working on your chapter 1 homework now. All right, thank you all. Well, thank you and good night for many of you, but I'll stick around. I know at least one student had questions, all right? All right. So I'm asking some students if they have individual questions. Any questions? Thank you all, yes. But I'll stick around. I assume trig questions. Although I've talked with students about the meaning of life and so forth. All right, here we go. First one. Well, I can do it from scratch. If you'd like to tell me what you've done on the problem, I'm chatting privately with a student. Let's see. Let me turn this off here. All right. So number 8. Okay, I have the homework here. If you'd like me to show, you're welcome to show your screen if you wish, but it's up to you. It's not necessary, but it's up to you. 4.2, number 4. Ah, yes. Okay, this one here. Wait, no, sorry, number 8. Number 8. Sorry. Number 8. Oh, no, you don't have to show the work, but I think just for your notes, for your information, I think it's good for you to make a few comments, like remembering that sine value is y coordinate, cosine value is x coordinate. So no, on number 8, you don't have to show work, but you might want to make some notes for your benefit. Right. So no, you don't have to show the work on number 8, but I do encourage you to put little comments here or notes for your benefit as a student. Okay. All right. Anything else? Anything else? Oh, you're welcome. Yes. Okay, so why don't we do this then? Oh, good night. Yes. Why don't we pause? I'll come back in a couple minutes. So I'll be back at 9:35. Okay, so those of you who are left, if you have a question for me, I'll be back at 9:35 and we can gather our thoughts. All right, I'll pause for now. All right, so let's look at some problems here. All right, so now again, I am recording. If you would like me to pause it, that's fine. But I find that students really appreciate a recording of these. All right, so let's see, 4.2 and 21, yes. Oh, okay, thank you. Yes. All right, so all my notes are from 20B. All right, so 21, right? 21. All right, number 21. If sine of theta is that, find cosecant. All right, so let's do that. So in fact, I can type this in, although I'll use t for theta. All right, so cosecant of opposite theta, I'm going to use t for theta. Now, first of all, which functions are even, which functions are odd? Only cosine and secant are even. These guys are odd. The other 4 are odd. So what happens to this -1 factor in here, this negative sign? Basically, it pops out. Move this over here. So by the odd property for cosecant, cosecant of opposite theta equals the opposite of cosecant of theta, right? And then how is this related to sine? Well, the cosecant function, the basic cosecant function, and the basic sine function are that R word. They are reciprocal. So we're going to use a reciprocal ID. Equals the opposite of 1 over, whoops, sine of theta by the reciprocal identities. All right. Any questions thus far? Any questions thus far? So then, what's our answer going to be? All right. So it's going to be basically the opposite reciprocal of sine of t. So it's going to be the opposite of the reciprocal of. I gave you that sine of theta was -7/5, but an easier way to look at it is you're taking the opposite reciprocal of -7/5. It's almost like perpendicular lines. The answer is going to be +7/5, right? Because the reciprocal of -5/7 is -7/5, but we want the opposite. So we go to +7/5.
Okay, thank you. My concern was I didn't know how to show the work. That was it.
Oh, I see.
I understand it was this one was an odd fraction.
Right. So I could tell that you sort of did the gymnastics in your head, but you're going, how do I show it? Well, here's how you could do it. Where I'm asking you to find this. When in doubt, look at the expression I want you to find or simplify, right? And see how you can express it in terms of this other thing you're given. So here you see that I'm relating cosecant of opposite t to sine of t, right?
Yeah.
Right,
Okay.
and that's a good strategy. Right.
Thank you.
Oh, you're welcome. Yes. It's quite possible that on an exam, I'd accept answer only. But you know, when you're doing either a test or homework, it's good to show work. It's good to have a sense of how to show your work, because let's say you're a tutor, right?
Yes.
A good example is when I'm grading, I might use as my guide. Well, if you showed this to a competent student, would a competent student understand what you were doing? Right? Good test. Yeah. Like
that was the concern. I knew it's going to be an odd fraction, but this is good work to show that. That's why we need it.
Right, right. What does it mean? Right, and it's good practice. So, so
Okay.
even though you kind of have the idea, one thing we do in our pre-calculus class is that you're formalizing your ideas. How do you actually write your ideas? And it's tricky sometimes, isn't it?
Yeah, this is a good stretch. Thank you.
It's very good, very good.
Yes.
Any other questions?
No. So
Now, if you like, I could come back in 3 or 5 minutes. Do you think you may have other questions later on tonight?
no, I think that's the only question I wrote down for when I was doing this. So.
Oh, okay. All right. So let's see who else is here. We have a couple people. Okay. So I'll come back at 9:42. Check on people. So I'll be back at 9:42.
All right.
And just kind of check on everyone, see how everyone's doing.